Then, as I said, these are the main collaborators that have been working with me, my graduate students, Ridoy Defna and Kevin Gonzalez Quesada. And I will emphasize mainly the studies that you can see in these papers. This is a new theory for spontaneous breaking Lepton barrier number and Majorana neutrinos and dark matter from anomaly cancellation, and also a theory that can predict the low scale system mechanism. Now, the main goal of this theory, of this talk, is to talk about this theory for neutrino masses where the symmetry breaking scale has to be low. Then there are a lot of things I could talk about this. You can see I could talk about anomaly cancellation and when the neutrinos are Dirac or Majorana and the connection to having a dark matter candidate and other signature like CP violation, baryogenesis or collider signature to look for electron violation or collider, no? But then again, even before that, I will try to emphasize and I will try to make few comments about the standard theories that most of the people study. And I hope that after this talk, you are convinced about how appealing these new theories are. Now, you know that these two questions here are very important for our community. We know that neutrinos are massive for a long time, and we have no clue what is the mechanism for neutrino masses. And we will be really happy to test and discover the mechanism for neutrino masses. Then, before I go to the technical part, let's, we have to remember we have no idea how neutrino masses are. They could be Majorana or Dirac. And this depends a lot of the degree of freedoms that we have in the theory. But it's much better if you write a theory that can make a specific prediction for the nature neutrino masses. Then in the case of Majorana, I will talk mainly about Majorana. We have huge number of mechanisms that we study for more than 40 years, from the canonical system mechanism for Witten mechanism and many, many other things. And we have a lot of theories for physics beyond the standard model where we can actually understand the origin of neutrino masses. The only problem with these theories is typically the scale can be anything or has to be very, very high scale. And then the testability of these ideas are, it's very hard to imagine we will have access to these high scales. But these theories, could describe, are very appealing and they make other predictions that are also appealing for the community. But it's depressing that we know about neutrino masses for a long time, and most of the theories that you write down tell you that the scale can be anything or has to be very, very, very high. Then, this is everybody in this workshop is expert. I don't have to discuss any thing that you know. But let me remind you that the canonical system mechanism, type 1 CISO, it's just a toy model, doesn't tell you pretty much anything, just tell you that if you have an extra degree of freedom, the right-handed neutrinos, you can, if they're very heavy, or not necessarily they have to be heavy, but if they are present, you could achieve Majorana masses for neutrinos. It's just that the scale, you pretty much don't know anything about the scale. If you assume that the M Dirac is around the electroweak scale, the scale has to be huge, but generically doesn't predict anything because it's just a toy model. This can be appealing and can be appealing getting this from grand unified theory, but still having high scale CISO, it's not clear that we will know about this in any experiment. As I said, if the scale is maybe low, then we can dream about the stability, looking for same sign like leptons and colliders. One maybe appealing scenario is that, if you have right-handed neutrinos for free, you can gauge B minus L, and then you have a new gauge boson that allow you to produce then a collider, in particular the Large Hadron Collider. And you can look for same sign Lepton signature. Maybe this is a way, but again, here, since you don't know what the scale is, you have to be super lucky to have any idea, to look for, to hope to see something. Now, before I go to the main part of my talk, let me talk about what we call the standard paradigm. Standard paradigm has been there for even before I was born. It's in 1974, Pavel and Salang wrote the beautiful idea of matter unification, where basically you try to understand how to unify quarks and leptons, and then they are just fermions, and they can live together in the same representation. Every time that you unify matter, lepton number is explicitly broken at the scale where this unification is happening. This is just partial unification. You could, later we knew about how to do SO10 and many other things. But the simple idea of matter unification by Patrick Salang already is making a prediction, is that you should have right-handed neutrinos if you want to complete the multiplet. This SO4 symmetry is very beautiful and is making also a prediction that if you think about seesaw mechanism in this context, actually you have to think about seesaw mechanism in this context, because the points that M Dirac here is predicted almost has to be very close to the upward masses, and then you have to implement seesaw mechanism and write everything. But the fact that the M Dirac is basically the upward masses, everything has to happen at the high scale. And okay, because neutrino masses doesn't allow you to do something different. And of course, if you do this in SO10, it's even worse because you have even more constraints. But the idea of Patrick Salang is very appealing, and it's in my opinion, the really most appealing idea that we have to understand how the right-hand neutrinos were predicted for the first time. This is actually the first theory that was written down for physics beyond the standard model in particle physics. However, if you think a little bit more about quark-lepton unification, together with my collaborator Mark Weiss from Caltech, we actually try to understand how really we could lower the scale, because the idea is so appealing. You unify matter, and you have the right-handed neutrinos there predicted, and you can ask the question, how I can generate neutrino masses and allow the scale to be low? Actually, you can do that if you have the inverse seesaw mechanism. If you add extra degree of freedom, S is a fermion, and chi is a scalar field, it's just breaking the SO4 symmetry. In this case, you actually, you don't have to do anything more. The exact form of the mass matrix that typically people put by hand in inverse seesaw is defined by the SO4 symmetry SO2 and U1R. And in this case, having inverse seesaw allow you to lower the scale. You are not constrained by the seesaw, by the huge constraint that you have between the M Dirac equal to mu, and the neutrino masses can be small, because the mu parameter that is protected by a symmetry is actually can be small, and then you can actually lower. You don't have to break SO4 at the canonical seesaw scale 10 to the 14, 10 to the 15. However, still, the gauge bosons that live in SO4, and in SO4 you unify basically QCD with B minus L, and then there are Berto quarks there. They mediate new processes like K long going to E mu, and the scale cannot be below 1,000 TeV. But at least you go from the canonical seesaw scale 10 to the 14 to 1,000 TeV. 1,000 TeV still is high scale, but I don't have time to talk about all the phenomenology of this theory, but you can see this reference there, where you can actually see for example, the Higgses, the decays are highly connected, because since you have matter unification, the new Higgses can decay to BB bar and tau plus tau minus, and the relation is basically factor 3, which is a color factor. And there are a lot of things I could say that, but actually the theory that we call low scale quadrilateral unification cannot typically describe physics below the 1000 TeV, unless, of course, you start doing more gymnastic, okay? But this is actually interesting because, again, it's taking the idea of Patti Salan and try to do your best and realize that the inverse seesaw can be realized in a simplest way without putting any extra symmetry in the game, and you can lower the scale for SO4 breaking from the canonical seesaw scale to 1000 TeV. Now, inverse seesaw is very peculiar. That's why you're allowed to do that. However, I am not giving this talk to talk about the standard paradigm. I would like to go back to my main goal, that is to study theory for neutrino masses even at lower scale than 1000 TeV. Now, this is something that I have been doing for a while, and this year I was able to actually find a new solution that allowed me to define a theory for Lepton number as a local gauge symmetry and study the spontaneous breaking of Lepton number as we do in the standard model with all the gauge symmetry that we have. And in this case, you just have to go back and forget about everything that we know about theory for the high scale and just do something very simple. You just say, let me take the Lepton number, total Lepton number as a local gauge symmetry. You know how the different, multiplying the standard model, we had 3 copies of L, Left, and ER, and you can work all the anomalies, and you find that there are 4 anomalies that are not 0, and you try to find the simplest solution to cancel all the anomalies and make sure that you are able to generate masses for all these new fields. Make sure that you don't get a mess. You don't make a mess in cosmology. You don't get any weird field, kind of decay, and find a solution that is very, very simple to make sure that after that you understand the spontaneous breaking of Lepton number and see if you can learn anything for neutrino masses. The solutions that, at least 2 of the solutions for anomaly cancellation have been there for a while. And the simpler one that was the first that we actually proposed is, if you are ultra conservative, you don't want to change the type of representations that you have in the standard model for leptons, the only thing that you can do is, you can do just Bertholli leptons. The quantum number for them are, the same as we have in the standard model. It's just that they are Bertholli under the standard model, and they are getting mass, not from the standard model Higgs, they are getting mass from the new symmetry breaking scale. And then if you say, okay, still I am speculating, I am writing a new theory, better I try to find the simplest theory. When I say simple theory, I am talking about the theory that has the minimal degree of freedoms that allow me to cancel all the anomalies and generate masses for all the fields and understand that, write a realistic theory, not a toy model. And, you can see here, and the minimum model I proposed this year, which has only 4 representations, and we'll mention later. Now, the striking thing about this is that when you take this idea very serious, because we know that, the standard model tell us, you have this symmetry there. Lepton number is just accidental global symmetry broken by SO2 instantons. But we know that is key for neutrino masses. Then you gauge, you try to understand the anomaly cancellation. And doesn't matter which solution you find. I mean, simple solution where you can actually generate masses for everything. You find something very interesting is that typically you will get a dark matter candidate, generically speaking. And this is interesting because this something is a bonus. It's something that you are not planning to do in the beginning. If you go back to the standard paradigm, even we like a lot all the matter unification or grand unified theories or other things, these theories never predict a dark matter candidate. you could implement maybe the Pechek-Wing mechanism and other stuff and symmetry and have, you can do that. In the past, actually, I did something similar, but generically, you never will get a dark matter candidate in these standard theories that we have for neutrino masses. Here, again, these theories are very simple, and anomaly cancellation, when you do this exercise, tell you that you can have a dark matter candidate. Therefore, cosmology can put some constraints, and the answer that you get is that the fact that if you don't want to overclose the universe or get more Rayleigh density that is allowed, typically the symmetry breaking scale for Lepton number has to be low. And then this becomes something interesting because there is a nice connection between cosmology and particle physics here that allow you to understand the original neutrino masses at the low scale. Now, the first scenario, which is not the minimum, but it's the most conservative, if you think about quantum numbers of the new fields, I am using a different notation here, but these are just Bernoulli fermions. They are transformed exactly as in the standard model. You have the right-handed neutrinos, and you have these three pairs of Bernoulli leptons. They could have different lepton numbers, but the anomaly cancellation forces you to establish that L1 minus L2 is -3. And then you can study different possibilities. I will discuss only the case where the dark matter is a Majorana fermion, where L1 is minus L2 equal to 3/2. And therefore, but the phenomenology in the Dirac case, here when I say Dirac, I am talking about the dark matter candidate, which could be a combination chi-L and chi-R, because it's the only two fields that don't have electric charge. In the doublet, there is something without electric charge, but direct detection will tell you that this is not maybe the great idea. Also, something interesting that this chi-L field is always present in all the solutions that we found for anomaly cancellation. Is that doesn't matter how you cancel the anomaly. I mean, the simplest solution that you have there, and you are able to write the consistent theory, chi-L typically show up in the theory and can be a dark matter candidate. Now, as I said, you have to be able to generate masses for them, and then you need to introduce a new Higgs, and this new Higgs will have lepton number equal to 3. I will remind you that in the standard model of particle physics, lepton number is broken by SO2 instantons in 3 units as well. S has 3 units of lepton number, and you are able to generate the masses for all the new fields. If here I want to study the case that the neutrinos are Majorana, you have a second field which is the standard field that we introduced for the seesaw mechanism. But the degree of freedoms are right-handed neutrinos at these Bernoulli leptons. Again, I will go back later to the minimal model, but this is the model that is looks very similar to the quantum numbers that we have in the standard model. Then, you have the usual seesaw. It's just the new thing here is that the right-hand neutrino mass is related to the mass of the new gauge boson. And that is good because if you find a way to constrain the mass of the new gauge boson, in this case, I will show you that it's constrained by cosmology. Therefore, here you have a low scale seesaw. The theory, of course, doesn't predict any Yukawa coupling, but it's interesting that you are able to put an upper bound on the symmetry breaking scale, and this gives you an upper bound on the right-hand neutrino masses. Therefore, you have a lower scale seesaw that also you didn't expect. The Higgs sector is the standard model Higgs plus the 2 Higgses. When you check carefully, you realize that there is also a pseudo-Goston boson that typically we call this a Majoron. It's not a dark matter candidate in this case because he will decay. The couplings to matter is suppressed only by the new symmetry breaking scale that is not very high, and therefore we can actually study the property of this. But again, let me emphasize something. Even if this is not a workshop about dark matter, you see every day papers about dark matter. You can build, toy models and so on, and you do, all the exercise of dark matter. But I think you can write a number of papers, I imagine, doing these things. Here, what I like is that you just want to do something very simple, study the spontaneous breaking of symmetry that we have in the standard model that is key for neutrino masses. Anomaly cancellation, say, here, I have a gift for you. You can have a dark matter candidate. Then you can study that. Here, I'm showing the case of Majorana. And then you study, all the annihilation channels and study here. Typically, the most generic channels is annihilation to the new gauge boson and the physical Higgses. Also, the Majoron is there helping. And then if you do the full calculation, I give you one example here. You find a region that is not so generic, that is around the resonance region where you annihilate basically to leptons. And the other region where basically you annihilate to all the other channels, but the annihilation to the new gauge boson and the Higgses is the dominant one. Here you cannot go below this line because you will be in conflict with perturbativity of the Yukawa coupling. This is also interesting about this theory. The dark matter is also getting mass from the sensitivity breaking scale. Therefore, if you start pushing the dark matter mass, since there is a connection in the symmetry breaking scale, you will be in conflict with perturbativity of the Yukawa coupling. Therefore, you have to live in this region here. But the interesting thing is that if you don't want to be in this peculiar resonance region, the symmetry breaking scale or the mass of the new gauge boson has to be below 10 TeV. And then, you don't have to live there. You can live below that. The collider bounds, in this case, the left bounds are strong. But, it's nice to see the cosmology tells you better you live below a 10 TeV, generically speaking, if you don't want to overclose the universe. The value of the gauge coupling you can change. You can increase a little bit if there's some awesome perturbative limit which are different from the usual thing because the Higgs has Lepton number 3 and you have to check. But the scale doesn't really change so much. It's just multi-TeV scale. Again, and this is interesting because, as I said, it's a gift that you get from the theory. And the key point is that this type of theory tells you that the scale for spontaneous L breaking must be below the multi-TeV scale. Then you can check direct detection here, the main contribution through the Higgs. This paper was written before the new bounds for LC, but you can check all the scenarios and when you don't even need a super small mixing angle between the two Higgses to satisfy the direct detection constraints. Then there is no anything that you have to assume a small. Okay. Now, as I said, this theory is also predicting a pseudo-Goston boson that's called the Majoron for historical reasons. And the Majoron here, it behaves a little bit more like an axion and a Majoron because can decay to neutrinos and can decay to photons due to the fact that one loop level, the Majoron coupled to all the new fermions, and you can put the photons, and then you can compute that one loop, the coupling to photons. And it's interesting that when the Majoron is heavier than 1 GeV, it will decay mainly to gamma gamma. And every time that you have something like that, you have to check the lifetime. Then if you have a lifetime around BBN, you have to be careful because there are a lot of bounds. And therefore, here I show you basically two scenarios for, the prediction here for the lifetime depends a little bit of the mass of the new fermions are inside the loop that is generating the effective coupling of the Majoron to photons. And therefore, but basically tell you that the Majoron should be, about a few GeV if you don't want to be in conflict with BBM because you will destroy helium or the deuterium and you will make a mess. And then BBM actually put a nice bound on that. Something also that I didn't expect. Something that I will not talk too much about, But basically here, the only collider we have now is the LHC for now. You can study the production right-hand neutrinos through the Higgses. It's not so easy because, the production cross-section is not so large. But at least, maybe if you have very high luminosity, you could see, but it's actually hard to look for in this case, unless we are super lucky. Okay. Now, as I said, the theory that where I define the Lepton number as a local gauge symmetry is super simple. And every time that I do this and I try to cancel anomaly, I get a dark matter candidate. And cosmology telling me that the symmetry breaking scale should be low. Therefore, really here you have a nice connection that tell you that the scale has to be low. And therefore the experimentalists could be, happy to look for at least to feel more confident that there is a hope to see something, because if the scale is the canonical scissor scale, I don't see how you can be optimistic about that. However, there is a model dependence here because depends how you cancel anomalies. And I told you, I believe we found all the simplest solutions for anomaly cancellation. But for my surprise, this year I found the simplest solution that I know for the anomaly cancellation. And before I show that, I will to remind you that the previous model, it's just, you want to be conservative, you want to put just Bertholli leptons as we know in the standard model and achieve anomaly cancellation and study the phenomenology of that. And it's also, you get the prediction that you have a dark matter candidate. It's just that the new frames are different, looks very similar. But if you are ultra conservative, at least I try to be conservative. I try to find the simplest thing you can do for any speculative idea for physics beyond the standard model. In this case, I will not talk about baryon number, but you can do the same for baryon number. You find that if you study the anomaly cancellation again carefully, for my surprise, you can cancel the anomaly with only 4 fields together with the right-hand neutrinos. Huh? And these 4 fields, this KL appears everywhere. You just change a little bit the lepton number. And these are like leptons, when I charge the leptons, just the lepton number is different, but that this is just a generalized symmetry. And plus, you have a triple FSO2 in 0 hypercharge. They are not really exotic. It's a triplet. And we have seen this type of fields in many theories. It's just the nice thing about this is that only 4 fields are able to cancel all the anomalies and together with the right-hand neutrinos and be able to, to do the job even for baryon number. And then I will tell you a little bit about this. Basically, you have to do the same exercise. You have to generate masses for the new field. Very simple. The lepton number for the new Higgs is different. It's not 3, it's 3/2. And you can, you have to worry if the new fermions can decay or not. The fact that the new charged leptons, they have a different lepton number, you have to make sure that they decay away and they don't make a mess. They are not stable. And there you can do that in the simpler way if you have a scalar field that allow the psi to decay to the standard model charged leptons. And once you do that, you can avoid this coupling between KL and UR. Then, of course, you will get the usual couplings, and I write everything all the way to dimension 5 just for fun. And now the phenomenology of the theory depends a lot if this new field get a BEF or not. Doesn't need to get a BEF. Yeah, the only thing that you need is the decays away. The new psi decay away to the standard model and the psi. But the phenomenology will change. For example, if psi get a BEF, you can realize that once you integrate out the chi, in this case the chi is not a dark matter, you realize that the mass matter for the right-hand neutrino has rank 4, a rank 1. Only one of them will get a very heavy mass at the TV multi-TV scale. but the others will not get mass from this symmetry breaking scale. And then you get a spectrum. The neutrinos is interesting because you will get a 3+2 line neutrinos, because the two other right-hand neutrinos only will mix with the standard model neutrinos. And this is interesting because, again, also in any theory that you write for physics beyond the standard model where we understand neutrino masses, it's very hard to predict live right-hand neutrinos. I mean, you can put by hand, you can do phenomenology, that is fine, but I'm talking a theory that do this for, as a bonus, as a surprise, something that can really surprise you, okay? As I said, the phenomenology of this depends a lot of the BEF. If you don't have...
Pavel?
Yes.
You have 2 minutes.
Very good. Thank you so much. If the phi doesn't have a BEF, neutrinos are Dirac. Okay? We like or no, they're Dirac. We have no idea if they're Majorana Dirac. And then in this case, they are fantastic bounds from N effective because, now they can be produced through the C prime and they can be thermalized at high temperature, and you can compute the effect of the impact the N effective could give you here. Actually, the bounds are actually stronger than the left bounds in this case. Then you can do also the fact that chi doesn't decay in this case. You can do the usual dark matter phenomenology, and again, the scale for spontaneous L violation must be below the multi-TV scale. Here, as I said, the N effective will play a really important role. And since I am on time, I will like to summarize in this way. Again, there is nothing wrong with the standard paradigm that we have for neutrino masses. And most of the community think that maybe they should be Majorana because the ideas like Patti-Salang or grand unified theories tell us that they should be Majorana. But since all these ideas are just ideas, we have no idea, if these are really things that we will discover. Here, I just try to tell you that doing something is very, very simple. Taking the standard model, taking even more serious the standard model and check the symmetries. Lepton number is the symmetry that tell us what is going on with neutrino masses. If you take that symmetry and you say, okay, let me make that symmetry local, let me do a spontaneous symmetry breaking. Before I do that, I have to cancel anomalies. And I show you that, which are the simplest solution for anomaly cancellation. When you check the theories, you realize, oh, look, I have a generically dark matter candidate. Then cosmology tells me the scale cannot be low. Therefore, the symmetry breaking is happening at the low scale. And there is a really hope here to test because the seesaw mechanism is actually happening at the low scale generically. As in the first part of the talk, I discussed the kind of a scenario that looks similar to, the representation looks similar to the standard model leptons. In this case, the neutrinos is a Majorana fermion, but again, the symmetry breaking scale is low. And didn't have time to talk about other things. And in the second part of the talk, I try to show you something even more conservative is that let's write down the simplest possible theory with this idea, with only for representation the right-hand neutrinos, and show you that there are two scenarios. The neutrinos could be Dirac, and you have a 3+2 spectrum, or the neutrinos can be Majorana, you have a 3+2 spectrum. If the neutrinos are Dirac, also you have the dark matter and the symmetry breaking scale has to be low. Then thank you so much. I apologize, I cannot be there.